using a rope parallel to the ground. He applies 170 newtons of force, and a 30 newton force of friction opposes his motion. How fast is the box moving after it travels 30 meters? So the first thing I'm going to do is begin the way I usually begin, which is by drawing a picture. So I've got a box, and it's being pulled by a rope parallel to the ground, and a man is pulling it. And initially, we don't have any kinetic energy. We presume we're starting from rest. There's no gravitational potential because we're not moving up and down relative to the surface of the earth or the ground. And there's no spring and straight, so there's no elastic. So that is going to be a 0. At the end, we know that he's going to have some kinetic energy. We're not sure how much, so I'm just going to put an open box for energy account. And we also know that he's going to have some energy in the thermal account because there's friction. So the question is, where does this energy come from? And it has to come from the man doing work. So we know that work is being done on the system by the man, and that can only be done if the man is outside the system. So our system cannot include the man. Otherwise, no work can be done because work can only be done external to the system, and that energy has to come from somewhere. So the next thing I can do, now that we've defined our system, is just the box, and we know where energy is going in terms of our accounts. We know that initially work is being done on the box by the man, and it's going to kinetic energy and thermal energy. We don't know how to figure out thermal energy yet. That's something I'm going to teach you right now. So the work done by the man is the force that the man exerts on the box. We learned this in the fall, times the distance the box travels. The kinetic energy is 1/2 the mass times the velocity squared of the box. And now thermal energy actually comes from work done by the force of friction. So this is going to be the force of friction time on the box times the distance the box moves. So I'm just going to rewrite this up here so that when I plug in numbers, you'll know where they come from. So the force the man exerts is 170 newtons on the box, and the distance the box travels is 30 meters. That is 1/2. The mass of the box is 40 kilograms, and we don't know the velocity of the box, so I'm going to leave it as a variable. And then the force of friction on the box, sorry, that should be a plus. Force of friction on the box is 30 newtons times the distance the box travels is 30 meters. So we know that the work done by the man when we multiply this out, is 5,100 joules, and that is equal to some unknown kinetic energy plus 900 joules of energy put into my thermal account. And so when I do the math, I find out that I've got 4,200 joules in my kinetic energy account. So I'm going to put that here. I'm going to put it all the way on the top. So that is 4,200 joules. That means each line is a little bit less than 1,000, or a little bit more than 1,000. And so in my thermal energy account, I'm going to put it a little bit below. I've got 900 joules. And so now my bars are correct. And last thing I need to do is figure out the velocity. I know that 4,200 joules, which is my kinetic energy, is 1/2 times 40 kilograms times velocity squared. And I solve that for velocity, and I find that velocity is 14.5 meters per second.